All right. Good afternoon, everyone. I'm sure you all had a great lunch, and I'll try to ensure that we don't get dozed off in my session. It's been a great conference this year. Been here a couple of times. Every year it just gets bigger and better. In the same venue last year, one of my colleague, Joseph Lynch, was talking about iterating stateful services in the cloud. And we got pretty good feedback after the talk. That is why we decided to get into much more details of how we provide smoother tail latencies in our stateful services at Netflix. So that's what I'm going to spend my next 50 minutes of my time here. I'll start with the introduction of stateful services at Netflix. And I'll get into the concept of change. How is it related to the stateful services? And I'll talk about benchmarking stateful services and how Netflix applies these benchmarking techniques in our stateful services. I'll walk you through all the tools and techniques that we built and the mental models that we built around providing smoother tail latencies in a stateful layer. I'll also talk about some of the case studies that we have done by using one of these benchmarking tools and mental models. So without further ado, let me introduce myself. I'm Vinay Challa, Apache Cassandra committer, spends most of my time with distributed database at Netflix. I manage data abstraction platform team as part of platform team at Netflix. What do we do? I'm sure all of you are Netflix subscribers. Otherwise, I can throw a sales pitch at it. So we are on a mission to entertain the world right from your couches. And we are available to stream across the globe, except few countries for obvious reasons. And Netflix is available in majority of devices across all these countries. Well, how does technology matter here? Well, technology matters the most here because right from your sign up to the binge watching experience, technology is the one that elevates the movie watching experience. It matters how you are interacting with the device, and it matters how movie is being shown to you. How does distributed system come into the play here? Well, to support millions of customers' needs, you need systems which can scale horizontally. And you want to give the same experience to every one of your customer, and distributed systems help you achieve that. But do they really help? Well, unlike like any other system, distributed systems also have a high tendency to work great to start with. But as you put into more load and as you put into more usage, then they exhibit cracks in their internal systems. And that's when you get into this question, do they really help? Maybe they don't. That's when you use the benchmark to build the confidence. Designing a system right from the scratch to work at any scale is a first step. But it doesn't just stop there. You need to use benchmarking to build the confidence to see if the system that you design is working as intended when you put it to scale. So in relevance of stateful services, let's talk about stateful services at Netflix. At a caching layer on the top, we have EV Cache and Dynamite. And the next one is a persistent layer, where we have Cassandra, Elasticsearch, Zookeeper, DynamoDB, DocumentDB, RDS. And at the bottom layer, for the longer durations of persistability, we use EBS and S3, and few more services as well. Then talking about the scale of these stateful services, in the overall footprint in numbers, we're talking about tens of petabytes of storage with hundreds of database clusters, making up to tens of thousands of nodes, using about hundreds of thousands of CPU cores across the stateful services. When it comes to scale, we operate at tens of millions of operations per second with the trillions of data records that are being persisted in our persistent store, and providing a sub-millisecond latencies for non-durable storage and low millisecond latencies for durable storage. So we talked about what stateful services and the scale of these stateful services, and see what kind of changes we do in the state at this scale. The first important thing is data model. As you onboard new use cases onto your existing services, or are working on new features, your data model often go through some changes, which involves maybe forklifting the data or doing changes to your persistent layer. And then the data access pattern. As the service is getting used more and more, maybe the customer behavior change, or maybe the service behavior change, which has a direct impact on stateful services. And some of these new features and new use cases might demand exploring new data stores out there, or building a custom data stores within Netflix to support all of these use cases. So with the scale that I mentioned, at the rate at which we are introducing these changes, how do we provide sub-millisecond latencies at a stateful layer in ever-changing ecosystem around the stateful layer? That's when I reference back to benchmark again to build the confidence. Benchmark when you develop, benchmark when you test it, benchmark during your continuous integration environment, deployment environment. Throughout the life cycle of a product, benchmarking is the key activity which helps you build the confidence. I'm not asking you to benchmark everything that happens in your production system, but think about benchmark as something that can catch things that can go wildly wrong in your production ecosystem. But why is it so big deal? Why is it a big deal to benchmark stateful services? The first thing is stateful services are a complex mixture of several components working together to achieve a common goal, right? And they are a hard piece of software because they involve state transitions. Let's say a user registered on your website and goes through certain stages, go through the billing, go through the payment, and go through watching the movie and rating your movies. This is all different state transitions that happen in your persistent layer. And benchmarking these states is a critical part of your stateful services benchmark activity, because as the state is transitioning, they have a different impacts on your different components of your stateful system. For example, when you started a new user, he doesn't have any rows in your table, maybe just one row. But as he watching movies or maybe making the payments every month, your secondary indexes gets bloated up. And that's when you exercise a different piece of your stateful service code, which you have never experienced in your dev or testing environments. Unlike stateless services, stateful services cannot be auto-scaled immediately. They take a lot of time because they have state, of course. You can't just terminate an instance. You can't just add an instance. They carry a lot of heavy state with them that needs to be transferred, which takes a lot of time. And another key thing that I want to stress here in benchmarking stateful services is the data access pattern. As I mentioned, they could change dynamically as your service usage is changing. Have you ever seen a service which is taking a request, gets one sort of request, and same request is coming like 1,000 times in a second, and you never see that request again? Yes, we all have seen that. Because none of you are benchmarking tools like either a random generator or generative models would not help you to benchmark those access patterns. You need a tool. You need these toolings which can help you to exercise those access patterns. That's a key part in benchmarking stateful services. And when it comes to data model, you might have seen many vendors talking about, oh, our service can do 8-byte request, 8 million in a second. Well, have you ever seen a same payload coming in a second 8 million times in your service in real time? You won't, because in a real time, those data model would be different, and the access patterns are different. And those are the numbers, those are the benchmarking numbers you publish on your website to sell your product, but not to run your service in production to have a seamless tail latency experience. So that is why benchmarking stateful services is a hard topic, and I want to stress on how we approach it at Netflix in this talk. The goal of this benchmarking is to build a mental model around your services that you are operating, and you know what you're getting into. You might not be foreseeing all the cases that are happening in production, but at least you know when you're getting into production what you're getting into, right? So how do, in general, stateful systems benchmark? First one is a traditional relational database. I took few examples here. This is not an exhaustive list by any means. TPCC is one of those common tools, and Apache, Cassandra, Lucene, being open source distributed databases, they operate in a different fashion. They benchmark it in a different fashion. And common distributed service tools like YCSP and Jepsen are few examples of that. With the TPCC, the Transaction Processing Performance Council has put together some of these guidelines on how to benchmark your traditional databases. Focus being heavily on database structures, database state transitions. They also focus on hotspots, which is a very common scenario you run into your environment because of lack of data model expertise or designing data model appropriately. And also indexability is another key thing, because when you persist the data, you want to query in all different dimensions, and indexing is one of the common way to achieve it. So TPCC focuses on benchmarking indexability features as well. And the ability to retrieve the data and presentation capabilities are also important aspects of TPCC. So the next different ballgame together is Apache Cassandra benchmarking, which is a open source distributed database. One of those tools is Cassandra Stress, which stress tests a very basic load testing for your Apache Cassandra database. Replay testing is another technique where you capture the production traffic, you put it into a new version of your database or a new configuration, do some sort of black box testing, see if state transitions is happening properly or not. And Harry is another benchmarking tool that is being worked on right now, which is a first testing tool for Apache Cassandra with the goals of performance, validation, and scalability with state transitions, and validation concurrent to state modifications. And you might have seen this kind of first testing and property-based testing in many systems out there, but essentially the similar thing that Apache Cassandra does, property-based testing, to assert some of these first testing and state transition capabilities to see if the database is going through the proper transitions as it is expected to. Then the other angle of tools is the YCSB, Yahoo's cloud serving benchmark, which is a standard benchmarking tool to evaluate the performance of distributed services. Two major components in it: YCSB client, which is a piece of code which generates a load for you, and workloads, core workloads are all different type of access pattern, like read heavy, write heavy, or a mixed load, stuff like that. Then the YCSB workload generator. I want to stress this slide here because I would like to reference one of the key things that I mentioned is about data access pattern. When benchmarking stateful services, data access patterns are the key, and YCSB focuses heavily on that by using this different distributions of workload generation, Zipfian, uniform, stuff like that. And the last one from my tool set is Jepsen, which is a tool by Kyle Kingsbury, a framework for distributed systems validation by introducing faults. It focuses heavily on network partition tolerance by introducing failure modes in clocks and in your system and also in the network. So far we talked about how typical systems approach benchmarking stateful service. Now let's see how do we at Netflix approach benchmarking. We built two mental models around benchmarking. One is active, and another is a passive benchmarking. In active benchmarking, the concept is simple. You generate a load, benchmark your system, and observe the metrics, understand the metrics, analyze your data, and either tweak your system or your configuration, or maybe tweak your code and benchmark it again until you reach to a point where you take a decision to go forward or to drop the service right there. So a mental model in this, you being center of it, you generate a load, you benchmark your system. Key thing is observing the metrics and analyzing that, and taking a decision whether to spend more time or make a call to not go forward with it. Simple. On other aspect, passive benchmarking, unlike active benchmarking, this happens in an environment where you're actually getting real traffic. So you put it on one of your production instance or an instance where you're getting most of the traffic and signals. You benchmark it. You observe those metrics and either tweak your configuration and add the resource that are missing, because AWS makes it easy to add whatever is missing, be it a CPU, core, network, memory. And when you're happy, you either gradually roll out to other availability zone and entire cluster, or take a decision to not go forward. So to put it into AWS Cloud mental model, you take an EC2 instance, you deploy your benchmarking in one of the instances, you observe the metrics, analyze the data, either tweak it, or when you're happy, go forward with one of these zones, deploy it in the entire zone, and do the same exercise, observe the metrics, and tweak it to proceed with the rest of the deployments. And this is where you take the advantage of distributed databases and distributed services, where deploying a piece of code in one node doesn't mean you are taking down the entire system. But there are, of course, trade-offs in these two models. Active benchmarking on one side is a very low-risk process because you're not getting into real production traffic. But you get low signals because, as I mentioned, none of these generative benchmarking models or random loads would give you actual signals that you get in production. On the other side, passive benchmarking would give you high signal because production is the actual load that you want to test against, but it's risky considering you're putting a benchmarking in production. So a quick summary, active benchmarking is a generative load to benchmark using generative or random load techniques. You observe the metrics, you identify the bottlenecks, you tweak your system, and take a decision. On a passive benchmarking, production load is a key load. That's the only place where you can actually get the right signals, deploy in one instance, observe the metrics, and do this process continuously all the time. So these are the two mental models that we work with within Netflix. But what is our philosophy in benchmarking, approaching the benchmarking, right? So the first thing is automation. All the benchmarking that I talked about, if you were to do it manually for every new use case that you are adding or every new feature that you're working on, that is not scalable. Your benchmarking has to be automated. Manual tweaks or hand-tuned configurations cannot scale. So automating a benchmarking is a first step. And then integrating it as part of continuous integration. Whenever you push a code change, config change, instance change, any change that is going through has to go through this benchmarking system. And this is one of those activities that cannot be stopped once your system goes to production and forget about it. It has to be a continuous learning process. As you put behind the scenes in cloud, everything is changing when you put your service in the cloud, right from your instances. Your instance network keeps changing. Your disk gets changed. Your load balancer gets changed. Sometimes a part of your code also gets changed in a platform environment where platform is pushing the changes behind the scenes, which you never tested, which you never benchmarked. The benchmark that you got yesterday might not hold true tomorrow. So benchmarking in production as a discrete action, not as a discrete action, but a continuous process is one of the key things in Netflix benchmark philosophies. So what tools do we have to apply these mental models and into the philosophy that we have. So on an active benchmarking tool set, we have NDbench, pre-flight check, and maybe one of benchmarking tools, because as I mentioned, they are one of active benchmarkings, or continuous integration benchmarking. On a passive benchmarking, we have AWS Bad I/O Detector and JVM Quake, which I'll talk about what these are in my next slides. And another key thing is declarative control planes, which I'm not spending most of my time today on declarative control planes, but we have many of our talks out there on the YouTube channel about what it means to build a declarative control planes. So the first tool that I would like to talk about is NDbench, which is a Netflix data benchmarking tool, part of our active benchmarking set. It's a pluggable cloud-enabled benchmarking tool that can be used to benchmark any stateful service out there. So as I mentioned, it's part of our active benchmarking tool set, which supports different data stores via plugins model, dynamically tunable configurations and load, and also the load patterns, which is a key in benchmarking stateful service, like random, sliding window, and zip theme. It's on our open source if you are interested in taking a look or using it. But why NDbench when we have many other tools out there? One of the key motives for NDbench is to make it run on an infinite amount of time. It's not like a start and stop. Like your production systems, they don't start and stop. They keep on running for the duration of your service, duration of your product. So observing these metrics all the time alongside of your production instances is a key thing here. And dynamically tunable configuration, because that's what happens in your production instance, because you change the instance type, you change CPUs, you change EBS bandwidth and stuff like that. But your service should still keep running and give you the metrics and insights of how this service is behaving in production. And a pluggable architecture enables you to work with any data stores that you onboard. And two key features that I want to stress on is auto-tuning and auto-detecting the data models. I'll get into that in the next slide. A quick architecture overview. So NDbench core is a center piece of component which generates the load, and you have plugins which are you can build all the data store plugins that you want and put it in a plugin layer, and you can configure the load patterns or build a new load pattern based on your production traffic. And to integrate with your metrics environment, metrics are also pluggable in this architecture. Auto-tuning, one of the key features of NDbench is referencing back to automating benchmarking. When you're benchmarking your service, let's say you pose a question, how much load my service can sustain in production with a tail latency, 99th latency of a millisecond, and average latency of 500 microseconds. At any given point of time, can we answer that? Maybe not, because you have different instance type from your development environment to the production environment. You have a different network bandwidth and usage behavior, so many variables in that. What NDbench auto-tuning does is once you put a system in any environment with configurations that you want, NDbench automatically generates the load to a level where you set SLO threshold. Tell me when my service is violating any of these SLOs. I want 99th latency of a millisecond and average latency of 500 microseconds. Tell me how many instances do I need? What kind of database configurations I need? And NDbench pushes the load to a level where a certain set of thresholds are being violated, and then tries to back off, because unlike stateless services, stateful service carry a state, right? So you put a system under load, you throw million writes at a database, it add all the writes, but it never flushed them, or it never populated them into the replica nodes. So they take a time to recover from that state. Even if you stop the traffic immediately, the next second your database won't be recovered. It takes at least another 5–10 minutes for it to recover, because it accumulated a lot of pending work that it needs to do. And NDbench gives that headroom for your services to recover. And it doesn't know when it recovered, so it gives it another try to see, are you alive? Can you satisfy my latency? Not, let me back off, exponentially backs off to a period of time when it finds a perfect load. This is what your service can do at a given SLO promises that you made. So automating that was a key, because you cannot hand tweak it and tune your service to get to a level where how much your service can generate a load. I mean, that's a tough question to answer, and IndiBench helps us answering that. Then the other point that I mentioned in my earlier slides is about data modeling. As data model keeps changing, you need to benchmark. But if you were to write a code for every data model change, that doesn't work. It doesn't fit into our philosophy of automating benchmarking. That's when IndiBench's auto-detecting data model feature works, where you can put an IndiBench, put a target of a data model and ask it to benchmark, and IndiBench automatically generates the data based on the data model, based on your tables, based on your indexes, and figures out the queries and generates a load for you, so that it's essentially automated. Because if you were to do it manually for every new use case, that won't scale. But is it easy to use? Let's see. So IndiBench is as easy as using a pre-baked AMI. You just spin up a ASG with the AMI, and your IndiBench will be ready to use. It exposes a web portal where if you want to manually do some benchmarking, one-off benchmarking, you can use this. You simply select a cluster, ASG where it's deployed. You select what kind of driver, which is essentially a data load that you want to generate, and the load pattern that you wanted to generate, and just click a start button and observe the metrics right then and there. But for you to integrate with your systems, you need an API. So that's what IndiBench supports, API integration as well, so that you can integrate as part of your continuous integration pipelines. In our case, we integrate this with Spinnaker pipelines. So how it helped us? This is one of the few works that delivered by IndiBench. When we were migrating from I2 to I3 instance type, we used IndiBench to do the side-by-side comparison of these instances. Also, when we are doing the kernel changes, when we are introducing new Kyber IO scheduler, we used IndiBench to do this benchmarking for us. Also, when you are doing any configuration changes, either your database configuration or JVM configurations, like CMS to G1GC, we used IndiBench to evaluate the performance of our data stores. But as I mentioned, AMI, the IndiBench is not just used as part of code and development process, but also as part of continuous integration pipeline. This is a snippet of our AMI pipeline in Spinnaker, which every code change or a config change that happens goes through this rigorous pipeline, where IndiBench, with a set of benchmarking sets that we have, benchmarks every piece of our code and publish the result. Based on that, we decide to either go forward or not. So overall, IndiBench at Netflix is used for active benchmarking system, to build the confidence on your new services, new data models, or new configurations, or new instances. And it's integrated as part of continuous integration system, so that every commit that you make goes through this benchmarking tool, and also used as part of deployment validation. So the next tool we have in our active benchmarking tool set is a continuous integration benchmarking. More than a tool, it's a concept of how we integrate benchmarking in our CI system. So I'm referencing back to the same one where IndiBench is used as an integration tool as part of our CI/CD pipelines. But since we have Spinnaker pipeline and all the tooling might be easy, but you might have many of these systems already, or even if you don't, unlike open source databases like Lucene. I took an example of Lucene, and here the approach of benchmarking is a key part. Lucene has a set of benchmarking suites that they run on every release. And as I mentioned, as part of benchmarking, not just benchmarking is important, but analyzing the data and understanding the bottlenecks and tweaking your workloads, tweaking your product is a key component of benchmarking. So Lucene, for every commit as the benchmark, so this is one snapshot of exact phrase query benchmark that they do. And they tag these metrics, these data with the release SHA and version to see how that particular commit has impacted their performance. Has it introduced any regression or has it bumped up the performance? You can easily correlate your commits with the performance when you are analyzing the data, something like this. So by the way, this is a great way to approach continuous integration benchmarking. Unlike in our NDbench approach, where we are benchmarking in every commit, what we are not doing today is analyzing the data, something like this. This is a great way to fully integrate benchmarking in CI systems. So far we have seen why to integrate benchmarking as part of development and CI system. So once your CI system gives you sign off, everything looks good. Is it good enough? Might not be. So that's when we'll talk about pre-flight check. So this is a bathtub curve of a typical EC2 instance, where there's a high tendency of an instance failure during the start of an instance for a certain period of time. And then for a period of, once that stage crosses, then it's pretty well, it performs pretty well for a long time, few years. And then at the end of its life cycle, again it exhibits failures in its hardware, network, and stuff like that. For you to fight with these tail latencies at the stateful layer, catching these early failures and the failures at a later stage of life is a key part. With any of benchmarking tools that we have seen, this is not possible, because we are not talking about code here. We are talking about environment. We are talking about ecosystem where it gets deployed. How do we approach that? So catch your instances at a pre-boot sequence. Benchmark as part of your instance launch or reboot. Integrate before all of your services are up and after your instance is booted. You benchmark your disk, you benchmark your network, you benchmark your CPU, you benchmark credentials, everything that your system is using. When you think that instance is meeting the expectations that you have, that is when promote it to in-service state so that your code can start executing and serve the traffic. If it is not, then just kill the instance. Then the question would be, well, it might delay your boot sequence. It might delay your startup process, which is good because you're not fighting, you're not missing your tail latency SLOs that you promised to your customer. How about disk during the flight? So code, commit, instance, environment, everything is benchmarked. Good. Once your service starts running, it could run for a year, could run for 2 years. What happens if disk goes bad during the flight? Isn't benchmarking code, commits, CI, CD, environment good enough? Let's take a look. So this is a healthy disk. Looks pretty good during the start. I don't see any demessage errors or any mount failures. Quickly ran a biosnoop to see how the latencies are to the disk. As you can see, majority of these i3 instance latencies are landing between under 100 milliseconds, right? 100 microseconds. Good, but suddenly this happens. As you can see, there's a good distribution of latency between 10 to 20 milliseconds, just reading from the disk. This is not good, but this happened during the flight. How do you, give this smoother tail latencies to your stateful users? That's when you use you know, since the disk is bad, let me just terminate the instance, get a new instance, copy the data from previous instance. Because this is a stateful system, it carries a heavy state with it. Unlike stateless service, you can just terminate an instance, and your auto-scaling group will launch a new instance, and you move on. It's easy to be said, but when you actually get to implement, when you are copying a terabyte of data from other instances, it takes forever. So that's not the right thing to do. That's when you use passive benchmarking methodology here to, to get out of this situation. So I'll talk about the first tool in our passive benchmarking toolset, AWS Bad I/O Detector. The goal is very simple. Any instance in our production environment, if it has any degraded hardware, it should not live more than certain time, random 10 minutes. Be it a local disks, networks, credentials, anything. If it is not meeting that criteria, if it is failing any of those promises, just take an action. So to put it into algorithm, you have check that happens all the time. File system failed. Is your file system failed, or do you have any I/O errors? Are you able to write to the disk? Let's say even if you are able to write to the disk, is it taking too long? If any of these checks are failing, then that instance is not healthy. You simply terminate an instance, like the way we did in pre-flight check. Only catch is you cannot do when the system is up and running, because what if the same disk, same situation happens across your stateful service? You terminate all the instance, you lose the data, there's an outage, you don't recover the data. That's when you need a control plane, which is what I'm not spending time this talk talking about declarative control planes, but control planes, having that control plane helps you to come out of this situation, because when any of these health checks are failed, you inform your control plane, hey, I'm not healthy, can you take care of me? Then the control plane looks at entire cluster and figures out, oh, maybe you are the only one, so you can be terminated. And if it finds out that so many others are also reporting the same error, it says it's okay to just live with a slow disk instead of losing the data. So the control plane, maybe with a simple locking service, can be implemented, a simple logic, something like this. And whenever control plane thinks it's healthy to do that, then it terminates the instance. So we got it covered so far: code, commits, CI, CD, instance start, and instance during the flight. Good. But we're not done yet, because when you're operating with the JVM, JVM introduces another variable. What if JVM has some crazy GC that impacts your tail latencies? So that's when I'll talk about JVM cake. So I'm sure many of you have already worked with JVM-based systems, and you know what is a GC spiral of death. Because operating any JVM-based system is a fun, and JVM introduces altogether new variables in your ecosystem. As we operate many JVM-based systems and databases, it is important for us to be on top of this as well. The question is, how do you predict JVM behavior and get out of the situation when your GC is something like this, where you're spending 20 seconds of your time just doing the GC than actually doing the work, maybe because of say point pauses or any other reason. And databases like Cassandra and Elasticsearch are so good, even if you ask it to return a million rows at the same time, it just takes a request and tries to work so hard, and it puts JVM under pressure. So here, the black rectangles are the ones where GC, the amount of time that is being spent in GC. As you can see, as soon as there is a query of death comes in, your JVM just busy doing the GC than actually executing your code. This is bad because it hits your tail latencies. And then you try to take a heap dump using JStat. You see it's 100% heap utilization, which is a bad thing. So you try to take a heap dump. Might not work all the time because your heap is busy. So then you take a core dump. Since it's too much of data, maybe 8 to 10 gigabytes, you cannot analyze on the instance. You ship it to off box, maybe to S3 or to another instance to open the heap dump and analyze. Meanwhile, you want to mitigate this process, so you terminate the JVM. I mean, you kill the JVM so that it restarts and you're back to business. Once you have the heap dump, you open the heap dump and analyze what is going wrong and figure out any query or anything that's wrong with the system, and you fix the system. But as I mentioned, the first philosophy is automating this process. It is not scalable if you are to do this manually for every time. But how do we automate this process? That's when we built a system called JVM Quake, which is a JVM TI agent inspired by JVM Kill, which introduces a very simple algorithm, token bucket algorithm, where if you are spending most of your time doing a GC rather than actually executing your code, you take a debt. Once it crosses certain threshold, then that's when you see, oh, you're going bankrupt. It's not a good time, and take an action. So on the left-hand side, you can see the JVM is healthy. Blue line indicates your debt, like how much of GC time you used compared to actual code execution time. And whenever it crosses the threshold, on the right-hand side, you can see that red mark where the bucket is full and you use too much of GC time instead of executing the code, and it's a time to take an action. And that's when you kill the process. But you need that data to analyze. So on an async fashion, you take a code dump, you kill the JVM, asynchronously push the data to S3 so that someone can analyze it. Meanwhile, your process is back online, your system is back online before it spends too much time doing a GC. So this is, just to put it to perspective, the dotted line in the middle is when the JVM Quake kicked in, as JVM is spending most of its time doing GC rather than actually actually executing your code. So after deploying JVM Quake, this is how a normal CMS looked like, healthy CMS and healthy G1 GC. And it's been running in our production for a long time. We recently talked about in our Netflix blog post. If you are interested in deploying it, it is very easy to deploy in your JVM systems. Take a look at our blog post and get back to us if you have any questions on that. So summary of tools so far. On an active benchmarking side, we talked about ND bench, CI benchmarking, and a pre-flight check. On a passive benchmarking side, which is important for you to fight with the tail latencies, is AWS bad IO detector and JVM Quake. So let's walk through some of the case studies we have done by applying these benchmarking models with the philosophy that we have. So I took an example from EBS, DynamoDB, S3, and some of our internal caching systems. So the first one is EBS. So majority of our stateful services run on i3 instance family. As you all know, ephemeral storage doesn't scale well because they take time. That's when we thought about how about EBS. Well, EBS is good, but which one though? There are so many EBS product categories. GP2, ST1, and all these EBS types have a radically different performance characteristics and also the cost. So that's when we said, okay, let's do our active benchmarking philosophy here, benchmark our system to see which one to use. We took a i3-2XL EBS optimized instance family which promises 212 megabytes per second aggregate bandwidth with 250 MB per second per volume GP2, and also 3 IOPS per GB because there is a IOPS limit per volume as well. Quickly, what we ran into is latency. As we started our benchmarking, we figured out instance family instance store latencies are not at all compared to the network attached like EBS, because you can't beat the physics. We saw instance store round trip times of 20 microseconds, whereas EBS we saw 130 to 370 microseconds for reads and writes respectively. Well, can we take a call? Oh, it's too much, let's not proceed with EBS. No, that's when we applied another strategy. Some number being good or bad doesn't make sense. We have to analyze the result. We have to analyze these metrics and understand the product and tweak it according to our use case. So that's when we decided, let's take a look at why our workload demands such a high latency from the disk. It could be size of the workload, or it could be the way you are using your data. What we have seen quickly with a read-only Cassandra workload on EBS, as you can see, majority of latency bucket you see around 500 to 900 microseconds. Whereas with instance store, it is hardly under 100 microseconds. Three things that we found out as part of this benchmarking: read ahead, disk scheduler, and also the working set size. With the read ahead, when you have instance store, specifically in this benchmark, it was Cassandra. So even with a low read ahead or no read ahead, it was performing all fine because the round trip latency to the disk was not too bad. But when you apply the same configuration that you have on instance store and put it to EBS, you don't see the same result, because that's when you try to understand the result. Okay, so it's a network storage, and there's a latency. So that's when we tweak the read ahead with a 32 kilobyte per that use case, and we were able to get the same performance throughput as instance store, because this tweak helped us getting more data ahead, which makes our compactions much faster. The next thing is a disk scheduler. As you can see on the graph, left side with Kyber IO scheduler, and on the right side without Kyber IO scheduler. That clearly shows having a intelligent IO scheduler also helps having a better performance on the network attached storage, and this was clear enough for us to go with the Kyber IO scheduler when using EBS. Then the third thing is working set size. As let's say you have a terabyte data in your database, you don't exercise terabyte data all the time. There is certain patterns, as I mentioned, data access patterns. If your traffic is during the peak hours, you exercise certain part of your data set, you bring it onto your memory, onto your caches, and you exercise that more often and throw it away. When you have an instance store, you don't need to pay attention to that particular component. But when you have something like EBS, you need to pay attention to the cost that you are paying based on the working set size. So ensuring that you have enough memory to have your working set size helps on 99th and 95th latencies. If you try to average all the metrics, they might look bad, but at the end of the day, when your 95th and 99th is also looking good, that's a good signal, right? So that's what we learned. On a latency, average might not look comparable, but 95th and 99th gets better. And EBS exercises a lot of CPU usage. And also how you're dealing with the data is an important thing. In case of Cassandra, the compaction strategy is the key to figure out are you exercising the disk heavily or less often or more often. What we draw out of this benchmark, the first thing is AWS makes it easy for you to, in case of EBS, you use more CPU than instance store. So you add more CPU and put that cost somewhere else and have the scalable data, which is EBS. So you can size your compute or disk appropriately, and a lot of management overhead can be reduced. When you are managing or operating a stateful service, carrying that state involves a lot of tooling in building their systems. That's why everyone tries to provide database as service, right? So EBS makes it easy for you to reduce that management overhead. And you can either use it for storage dense or heavily cached data set. But key learning that we can take away from this case study is identifying the bottlenecks, not going by the numbers that are published on database vendors or cloud services. Identify the bottlenecks and understand your product and tweak the product according to your use case, and that's when it starts working. And here we applied both active and passive benchmarking models. We benchmarked in an environment where there's no traffic with the models that generative models that we built in production. So we were able to tweak the configurations and come up with a golden set of configurations. That's active benchmarking. But when we put it into production, we used a passive benchmarking model where you put it on one instance, observe the metrics, let it run for some time because it has to go through a lot of state transitions, and slowly apply to other zones and other regions and other clusters. So this is a mixture of active and passive benchmarking models. The next one is a DynamoDB benchmark. So the use case was to benchmark a scenario where transactions are being used to write it to multiple tables. So you have a test setup of 30 IndieBench nodes reading against these tables. One table with 4 columns and 1 key column, and all other 4 tables with just 1 column. Each of them have about a kilobyte size. And we saw reads of 6,000 RPS at 10 millisecond 99th, and writes of writes at 1100 writes per second at 80 millisecond 99th. What did we learn? So 2% of our workload writes were failing because DynamoDB was under provision during that time. Even if you have auto-scaling enabled, sometimes it can take time, and that could impact your tail latencies. And another finding was DynamoDB server metrics might not show the capacity that you used up accurately, because when you are using transaction, they consume double writes, but they are not reflected in the metric. The fix was simple, just read the whole manual, and it is mentioned somewhere. You just need to read the manual. The next one is Amazon S3 benchmarking. The goal was to maximize the available instance network bandwidth to see if the bottleneck was in our service or was in S3. And we were able to maximize the network bandwidth on instance with a very simple benchmarking tool that I put in one of our colleagues' gist. What we found out was you can scale Amazon S3 up to 50 gigabits per second on a single EC2 instance. It could do more, but that's what we benchmarked for. The key finding was tune your clients and the access pattern or consumption to get there, instead of just taking a look at the number and say, oh, S3 is slow, we can't work with S3. So lessons learned: bottleneck could be your usage pattern or your access pattern instead of actually stateful service. And analyzing that benchmarking result and tweaking your access pattern could be the way forward. Next category is benchmarking caching systems. The focus was heavily on performance. Goal of seeing benchmarking your benchmarker and see how accurately we can measure the numbers. So with the IndieBench, we were generating 2.5 million requests per second on a 3 nodes and a 48 nodes cluster, and we were able to get the latencies under 750 microseconds or 500 microseconds, which clearly showed us that your benchmarking tool is not the bottleneck here, and measuring the latencies accurately is a key part of your benchmarking tool. So overall, from benchmarking philosophies, benchmarking tools, benchmarking techniques, and all the case studies, what I want you to walk away with is both active and passive benchmarking models are important, and they are equally important. And use your benchmarking to identify the bottlenecks, not to walk away with the numbers. Oh, this can do 1000 RPS. Doesn't matter. It depends on your use case. It depends on your access pattern. And AWS makes it easy for you to add any resources that are missing. And make it easy to benchmark, so that benchmarking should never be a burden to the developer, rather it should be a part of the whole development process seamlessly. So self-driving benchmark, auto-tuning benchmarks are the way to scale instead of hand-tweaked, hand-tuned configurations. Build a benchmarking repository like your test case repository. In a traditional way, you benchmark your service before getting into production, and you forget about it. But what is the key thing is benchmark is a continuous learning process. This can never be complete because in a stateful services, your data models change, your data access pattern change, your data changes, and every time you exercise different component of your distributed system. So building that repository of benchmarking tools, benchmark tool set is important, like the way Lucene does. Invest in a desire-based control plane because that helps you, build these passive benchmarking tools which are actually happening in production much more easy. Without having a push-based system or a desire-based control plane, it is really hard to build a passive benchmarking tools, unlike active benchmarking tools. Lastly, benchmark your benchmarking tools because you don't want your benchmarker to have the bottleneck when you're benchmarking your service, right? So with that, a simple takeaway is benchmark is a continuous development practice that should be part of your continuous integration and development process. This cannot be forgotten as soon as your systems are deployed in production. Thank you.